Hi there everyone, welcome back to my channel. In this video, we will be learning of alcohols and how to categorize them into specific groups. From this, we will learn how to oxidize each problem and name the products. This includes drawing each alcohol, categorizing each alcohol as primary, secondary, or tertiary, oxidizing each alcohol as many times as possible, and naming each product if there are any for each alcohol. Today's example is 3,3-diethyl 1-hexanol and 2-methyl 1-nonanol. But first, before we jump in, let's quickly review what we know about alcohols. In chemistry, an alcohol is an organic compound with an hydroxyl or OH functional group bound to a carbon atom that is saturated. For example, this is what an alcohol may look like. We see that the OH is bound to the carbon atom. Here we have some common functional groups. Some we've learned in previous videos and some we haven't. The goal of this is to try and memorize all the common functional groups. That way, when looking at a molecule, we'll be able to differentiate whether the molecule is an alkane, alkene, alkyne, an alcohol, an aldehyde, a ketone, an ether, an ester, and a carboxylic acid. We see the R at the end of every group. We have to know that the R is the rest of the molecule. It does not include the OH groups. Now, let's go through the process of drawing the alcohol 3,3-diethyl 1-hexanol. Remember that when we look at our molecule, we always start at the end. We see that we have an all at the end. Looking back at our common functional groups, going down the list, we see that we have an alcohol. We see that an alcohol has an OL at the end. Therefore, we know that we have an alcohol in our molecule. We know that our alcohol must look like this. Because there is an OL at the end, let's remind ourselves by putting an alcohol at the top of the list. On our next part, we see that we have a hex in front of the all. Referring back to our alkanes, we know that we see hex, which means that we have 6 carbons located on our molecule. Looking at the beginning, we know that the alcohol is going to bond to the first carbon. Moving right along, we see that we have ethyl. Looking back at our substituent list, we see that we have ethane or ethyl. This means we have ethyl connected to our molecule. Previous of ethyl, we see that we have di, which means that we have 2 ethyl groups on the molecule. Looking previous before diethyl, we see that we have 3,3. This means that the 2 ethyl groups are bonded to the 3rd carbon. Now that we have all our information, let's first draw the 6 carbons on our structure. We put this break here on purpose in the structure, right here, because we know that we have a diethyl group attached. Remember that if we have 2 same substituent groups, we can put them like this on the structure. Looks sort of like a cross. So now we count 1, 2, 3, 4, 5, 6 carbons on our structure. But what do we put here? Remember that at that first breaking point, it is not a carbon, but it's actually an alcohol located on the first carbon. Let's go back through our list and make sure that we have everything. First, we see the alcohol. It's bonded to the first carbon on the molecule, as shown here. Next up on our list, we see diethyl. So we know that there are 2 ethyl groups to the 3rd carbon. We know this because there is a 3-3 at the beginning of diethyl, so it is located at the 3rd carbon. Finally, we have our completed structure of 3,3-diethyl 1-hexanol. Now, let's go through the process of drawing the alcohol 2-methyl-1-nonenal. Looking at the end of our molecule, we see all. Looking back at our common functional groups, we see that an O-all is always an alcohol. Therefore, we have an alcohol on our molecule. Next up, we see that we have none. Looking back at our first 10 alkanes, we see the prefix none, which means that we have 9 carbons located on our molecule. Let's draw what that looks like. Next on our list, we see that there is a 1 in front of the nonenal. This means that the alcohol will be located at the first carbon of the structure. Technically, we could put the first carbon here or on the opposite side here. Let's put it on the left side. Next, we see that we have a methyl. Looking back at our common substituent list, we see that we have methane, or methyl. This means that we have a methyl group attached to our molecule. Next, we see that there is a 2 in front of the methyl. This means that the methyl group is located at the 2nd carbon. Let's draw what that looks like. Now we have our completed structure of 2-methyl-1-nonenal. Secondly, let's categorize our alcohol as primary, secondary, or tertiary. But what's the difference between primary, secondary, or tertiary? Primary alcohols look something like this. When the OH group is at the end of an alkane chain, an alcohol being at one position is a primary alcohol. Secondary alcohols look like this. When the OH group is in the middle of an alkane chain. Lastly, tertiary alcohols are when you have an alcohol on a carbon chain that looks like a cross structure. Before this, we must determine and identify the alpha carbon. The alpha carbon is the carbon directly attached to the OH group. Since we know that the alpha carbon is the carbon directly attached to the OH group, we first have to find the alcohol. We see that our alcohol is located here, so our alpha carbon is the one closest to it. Let's draw what that looks like. As we can see, the alpha carbon is directly bonded to one carbon. Therefore, since it has one carbon attached to the alpha, it is a primary alcohol. For our next molecule, we see that the alpha carbon is connected to 2 other carbons, so it's known as a secondary alcohol. Lastly, on our last example, we see that the alpha carbon is attached to 3 carbons, which tells us it's a tertiary alcohol. Let's quickly identify all of the alcohols. Now that we have the basics down, let's identify our alcohol. In our first structure, we see that the OH is connected to 1 carbon. This is the alpha carbon. Since it's only connected to 1, we can classify it as a primary alcohol. On our second molecule, we see that the OH is also at the end. It's connected to the alpha carbon, and the alpha carbon is connected to only 1 carbon, which makes it a primary alcohol. Thirdly, let's oxidize the alcohol as many times as possible. The oxidation of alcohols is the addition of a bond to oxygen in an alcohol. The products vary by type of alcohol. A hydrogen on the alpha carbon is lost. Since both of our molecules are primary alcohols, let's focus only on primary alcohols. On primary alcohols, we redraw the OH functional group going straight up and we show a hydrogen. Let's draw our original molecule and add oxygen to it. For our first problem, we have our alpha carbon here, which means there is one carbon attached. There is two hydrogens hanging off the alpha carbon. Let's redraw our alcohol, but the OH should be drawn straight up, just like this. We have two hydrogens here, so we're going to add a bond to our oxygen. Because it's a double bond between carbon and oxygen, it means that both carbon and oxygen have extra bonds. So we have to get rid of an alpha hydrogen, so we just have 4 bonds. Also, our oxygen only wants 2 bonds, and now that we've added another bond, we have to get rid of the hydrogen next to the oxygen. We still have a hydrogen left, so this means we can oxidize it one more time. Now we can oxidize it one more time. Let's redraw our alcohol product again from where we left off. Remember, we get rid of the alpha hydrogen again, and we need to add a bond to oxygen. This oxygen cannot accept any more bonds. We have to add another oxygen on the molecule. And because oxygen needs 2 bonds, we're going to add OH to the molecule. Like the last problem, let's first redraw our alcohol. Let's begin our oxidation process. First, let's redraw our alcohol, but remember the OH group should be drawn straight up, just like this. We have 2 hydrogens here, so we're going to add a bond to our oxygen. Because it's a double bond between carbon and oxygen, it means that both carbon and oxygen have extra bonds. So we have to get rid of an alpha hydrogen, so we just have 4 bonds. Also, our oxygen only wants 2 bonds, and now that we've added another bond, we have to get rid of the hydrogen next to the oxygen. This is our product. We still have an alpha hydrogen, so this means we can oxidize it one more time. Remember, we need to get rid of the hydrogen again, and we need to add a bond to oxygen. This oxygen cannot accept any more bonds. We have to add another oxygen to the molecule, and because an oxygen needs 2 bonds, we're going to add an OH to the oxygen. Lastly, let's name each product if there is any for each alcohol. Since we're dealing with primary alcohols, we know that we have the products of an aldehyde and a carboxylic acid. Here we can spot that an aldehyde has an Al at the end, and a carboxylic acid has an oic acid at the end. Let's write down the products of these primary alcohols, which is an aldehyde and a carboxylic acid for both, considering that they are both primary alcohols. Now that we know this, all we need to do is change the ending to the original alcohol to correlate with the specific product. We know that an aldehyde ends in Al, and a carboxylic acid ends with oic acid. So all we have to do is write Al in the place of Ol, and replace Ol with oic acid. Let's do the same for the other molecule. Here's our finished products for 3,3-diethyl 1-hexanol. And here's our finished products for 2-methyl 1-nonanol.